Transmitting complex software logic across physical wires as raw binary without structural chaos is the foundational problem of network architecture. In the late 1970s, the International Organization for Standardization faced competing hardware vendors building proprietary systems that could not communicate with each other. They needed a strict standard to enforce interoperability. The solution was the Open Systems Interconnection, or OSI, reference model. It established a common communication structure for all computer systems. This diagram shows the 7-tier architectural grid of the OSI model. It dictates continuous state transformations from the application layer down to the physical layer. Data does not simply glide intact across a network. It undergoes a rigorous process of encapsulation. Encapsulation is the addition of a specific header, and sometimes a footer, to the data received by each layer from the layer directly above it. Network functionality and security controls do not operate as a monolithic whole. They are strictly localized to specific layers within this stack. To implement secure network architecture, a core requirement for any Certified Information Systems Security Professional, or CISSP candidate, you must understand exactly how data is structurally mutated as it descends through these layers. We begin at the top of the stack, at Layer 7, the application layer. This layer provides the interface between user software and the protocol stack. The data then moves down to Layer 6, the presentation layer, where it is formatted so any OSI-compliant system can interpret it. This is also the stage for pre-network encryption. Next is Layer 5, the session layer, which establishes, maintains, and terminates the communication dialogues between computer nodes. It establishes communication sessions in one of 3 control modes: simplex, which is strictly one-way communication; half-duplex, which is two-way but only allows one direction to send at a time; and full duplex, allowing simultaneous two-way transmission. In practical application on modern TCP/IP networks, there is no distinct presentation or session layer. Those specific functions are handled lower down by the Transmission Control Protocol, or TCP, at the transport layer. This chart shows the layer-based network container names. Notice the top 3 rows. The application, presentation, and session layers all classify this initial network container strictly as a Protocol Data Unit, or PDU. This diagram illustrates OSI model encapsulation. Looking at the top 3 steps, you can see how the growing header block precedes the data payload as it moves down through Layer 5. Layers 7 through 5 prepare the raw software data for its journey. They format it, encrypt it, and define the rules of conversation, unifying the data into a stable protocol data unit. Dropping into Layer 4, the transport layer, triggers a structural state change. The PDU is now classified as a segment if it uses TCP, or a datagram if it uses UDP. Layer 4 defines the specific rules of the session, managing end-to-end transport delivery, sequencing, and error checking. This is the layer where security protocols like TLS operate. The container then drops into Layer 3, the network layer. A new header is appended, and the container is renamed again to a packet. The network layer is responsible for logical addressing, which means assigning source and destination Internet Protocol, or IP, addresses, and routing that traffic across different networks. The primary network hardware devices that operate at Layer 3 are routers. Routers use 2 broad categories of interior routing protocols. Distance vector protocols measure the path in hops, counting the number of routers to cross. Link state protocols gather performance characteristics like speed and latency to make the routing decision. We contrast those interior methods with exterior routing protocols. Path vector protocols, like the Border Gateway Protocol, or BGP, make decisions based on the entire remaining path to route traffic across massive autonomous systems, which are large collections of IP networks controlled by single organizations. The critical security implication for Layer 3 is route integrity. Routing tables must be strictly secured by configuring routers to accept updates only from other authenticated peers. Layers 4 and 3 take the internal dialogue from the upper layers and transform it into a targeted package, ensuring the data has the integrity and the logical directions required to navigate the global internetwork. This diagram shows the final logical formatting. Look specifically at the data link row near the bottom. This is the only layer where both a header and a footer are attached to the payload. At this stage, the container undergoes another state change and is officially called a frame. Layer 2 relies on physical hardware addressing to route traffic via switches. It accomplishes this by adding the Media Access Control, or MAC address, which is a 48-bit binary address written in hexadecimal format. The first 24 bits of this address constitute the Organizationally Unique Identifier, or OUI. The OUI is critical for security operations. It allows network analysts to identify the exact vendor or manufacturer of the physical network interface card communicating on the local segment. For the final step, the frame drops to Layer 1, the physical layer. Here, the container is converted into raw physical bits for transmission. The logical packet is now fully bound to hardware, converted into electrical, optical, or radio signals, ready to cross the physical gap between networks. Once those physical bits reach the receiving hardware, the entire process executes in rapid reverse, traveling back up the stack. The Internet Engineering Task Force defines this inverse action as de-encapsulation. This graphic maps OSI model peer layer logical channels. Notice the horizontal arrows connecting the protocol stacks. Instructions removed by the receiving computer at Layer 3 can only be understood by the equivalent Layer 3 that created them. This is peer layer communication. Understanding this mechanism is the foundation for mapping layered network defenses. We deploy MAC filtering and wireless encryption to isolate localized threats at Layer 2. We apply VPN encryption, like IPsec, to secure the logical routing paths at Layer 3. We use session protection, such as TLS, to enforce end-to-end integrity at Layer 4. For the security architect, the OSI model provides the exact engineering coordinates for deploying defense in depth. It dictates exactly where vulnerabilities live in the network stack and exactly where your controls must be applied.